Bonjour, bonjour à tous et à toutes. Je vais parler en anglais. هتحدث باللغة الإنجليزية لأنه في عنا أصدقائنا التاليين تيفهموا علينا. So, President of the Federation of Engineers and Architects, Mr. Arif Yassin, Mr. André Bekhazi, Member of the Higher Council for Urban Planning, Mr. Claudio Pascolucci, Director of the Italian Trade Agency, dear colleagues, friends, ladies and gentlemen. I am pleased and honored to welcome you at ALBA today for this seminar. The tragic and criminal blast of August 2020 at the port of Beirut has affected our urban heritage. As a paradox, it has also been an opportunity to unify the efforts of our civil society and the experts to protect, reconstruct, and restore the built heritage of Beirut. At the Beirut Heritage Initiative, we have been focusing on diffusing the principles of good practice to the teams on the grounds with the collaboration of the most qualified and enthusiastic professionals in restoration. And some of them are here among us today. In collaboration with S.r.l and with the Italian Trade Agency, we are committed to keep on sharing our experience and learning more from each other. My dear colleague and friend, Mr. Dr. Michel Chalhoub, has been key in helping us all understand the structural impact of the blast on the masonry built heritage of Beirut through his analytical approach. While the schools of engineering focus mostly on teaching reinforced concrete, I feel it is essential to introduce the stone masonry structural dimension, which have been neglected for 100 years, and discuss methods of reinforcement that are not intrusive and respect the properties of the buildings. As a counterpart to the essential reinforcement of the structure, I am pleased to welcome also Mrs. Karin Nahas, who will share her experience on restoring the decorative ceilings and walls of the Beiruti houses after the blast. These interventions, structural and decorative, are the alpha and omega of the restoration process. So we here at ALBA, at the same time, of course, we teach a lot of things from urban planning to decorative arts. So I think it's very essential for us all today to see all the process, so how a house is structurally built and then how the decoration comes in at the end, and people mostly see the decoration and they forget about the structure. So this is why I think it's very important for us today. And we will share at the same time our experience with our Italian guests who have, of course, a huge experience in this field, and we will be, of course, open to discussion. So you are all of course, welcome to ask questions, raise points, and discuss everything. Thank you all for attending, and yalla, let's start. Michel, the floor is yours.
Hello everybody, I'm Michel Chalhoub from District Solutions, a design build and research and development firm. Can you hear me now? Okay. So I repeat, I'm Michel Chalhoub from District Solutions, a design build and research and development firm. I'm pleased to be here to share our experience in masonry and to learn from your experience also, especially that we have many local and Italian experts. Thank you, Fadlo, for the introduction. Thank you, ALBA. Thank you, Italian Trade Agency, and S.r.l for being here also. So, as we all know, with more than 5 years of history, Lebanon is very rich in terms of built heritage. And this heritage most of this heritage is made up of like masonry. So there is a need to retrofit, to reinforce, to maintain, and to restore this built heritage. In fact, the subject masonry is very wide, and I will focus on the Lebanese built heritage, especially the one of the Beiruti houses, because it needs more time to cover all this subject. First, I will talk about the concept of structural restoring of built heritage. Then I will move to the milestone of a structural retrofitting, and I will focus a bit on the structural analysis of built heritage. We will see some proposal for reinforcement, and I will talk finally about monitoring. So I chose to talk about the medicine of built heritage strengthening. Why? Because every built heritage, every historic building is very complex in terms of history, phasing of construction, like building materials, technique of constructions, aging, and so on, heterogeneity of multiple parameters. So really we need to use some similar protocols of doctors to deal with our built heritage. The issue is that our patient is also, we need some geriatric medicine. First, if a patient will come to a doctor, he will ask him about the history of his health. So, are you a smoker? Did you have some surgeries during your life? And similarly, we do for the built heritage. Then the doctor will go for a clinical inspection. Then if he needs more, he will ask for a like X-ray or some endoscopy. So we can see similar photos from the medicine part and from the engineering part. At the end, he will go for the therapy, and here the therapy should be controlled and observed. So he will tell his patient, please come after 6 months, so we can do a checkup for your health. Now I will move to the milestone of the structural restoration of built heritage. First of all, we talked about the history of the building. Then we move to the site inspection and diagnosis, going from the visual inspection to the structural system identification, material characterization, soil, and we will focus a bit on the non-destructive and minor destructive testing in the field of built heritage. After that, I will present the structural analysis and especially the numerical modeling, the finite element modeling, nonlinear ones, and we will move to the proposal for reinforcement, and we will end by the monitoring. So this is a case study that we conducted on the SYDA sea castle, where we have found some document dating from 1871 and some of Calayan. We could prepare the construction phasing of this castle based on these documents. And we found also that there is, for example, a sandstone quarry not so far from the castle to produce the sandstone materials. Here we move to the site survey, and I'm showing two principal like tools, which are the photogrammetry and the laser scan. I chose these two ones in addition of the archaeological survey and traditional architecture survey, because these two tools like are very useful in monitoring. We can compare the actual state of the building or the monument, and after 2 years we will come and do the same and compare if there is some modifications in terms of displacement or movement in this monument. Here I move to the site survey, and first of all we have to make like a damage mapping. It means like we have to put on a paper, on photos, the cracks, the decays, based on some principle provided by ICOMOS or UNESCO. So here, for example, it's a case study, ongoing case study in Douma. This case study is from Beirut. After the blast, we can see at the bottom right the mapping of damage, and to the left like a zoom on an area where like an out of plane behavior has occurred. We can see the deformation out of the plane of the wall here. And we move now to the inspection and diagnosis. So first we will start by the foundations. In fact, the system of foundation of the Beiruti houses especially is like a foundation wall or like arches, the photo to the bottom right. In addition to the soil investigation that we all know for contemporary buildings or for soil investigation, we have to do some pits and to discover what is the typology of the foundation, if there is any crack, like for example the photo to the bottom left. And in some cases, like here, it is an ongoing project. we discover that there is a heterogeneity in terms of depth of foundations, typology of foundations. So this is something that makes a bit difficult to treat like a built heritage, not likely with contemporary buildings. We move, for example, for the inspection, and here also examples from Beiruti houses or Beiruti historic buildings. We did some inspection on the walls to see about the texture, and we discovered, for example, like rubble walls from the inside. It means like very poor mechanical properties for the walls, for the bearing walls, I mean. And here to the right, like the system of slabs, like a wooden slab, and the planks. So we need to check every single details, because the connection between walls and slabs are really weak in the built heritage of Beirut. Here we move to another example of a church, a very well known church in north of Lebanon, where we can see by our eyes a very big crack on the elevations, like in the bottom to the right. We can see also like a settlement of the pier and a sliding of the soil. All of these like parameters can give us a clear vision about what is happening in this monument or in this building. And so we can build on to move to other like steps, like for example testing NDTs or MDTs. NDTs mean non-destructive testing or non-invasive testing, or minor destructive testing. I will move now to the second step of inspection and diagnosis, which are the testing. And I will focus a bit on some useful testing for the seismic calculation or retrofitting in the built heritage. We all know the georadar, we all know the boroscopy, but we will focus on the sonic and the dynamic test, and also we will present the double flagjack test, which are very useful in masonry structure. Okay, here an example of the dynamic identification. It's the experimental dynamic identification. I know that many engineers make like model analysis, okay, on numerical software, commercial numerical software. But to do right, we have to check if our numerical model or digital model is really representative. For this reason, we have to make what we call the experimental dynamic identification. It means to know how our building is vibrating under a normal vibration or forced vibration. Here we can see the tool. We need some wires, a data acquisition system, the accelerometers. They are the key of the dynamic testing, and some connectors. I will show you some testing we have done here in Beirut. We can see the signal, and to the left, bottom left, the numerical model. It is a nonlinear numerical model, but for the model analysis, we are in the elastic phase. We can see the mode shape. It means how the walls are moving according to an earthquake. And to the right, it is the experimental output. It is a post-processing who demonstrates that the mode shapes are similar between experimental and numerical. We need this also to calibrate our numerical model. It means to make a sense for our numerical model to get good results. Now I will move to the sonic or ultrasonic test. We need this to know about the quality of our walls. The same system of the dynamic testing is here, but we add a hammer that we can see in the middle left. And to the right, we can notice like an output for the sonic testing or the ultrasonic testing. The one in the middle shows like a variation in the colors. It means like inside our wall we have some voids, and the one to the right is homogeneous after injection. We can see the injection process. So this is a good tool to know about the quality of our masonry walls. I will move now to the double flagjack, because this one is really very interesting, especially for from we can see on the right the strain curve. It means that we are knowing, or we are learning about the deformation and the stress of our wall. This is very useful because, as you know, here the masonry is made up of stone blocks or brick blocks and the mortar joint. So we need a homogenized behavior. So we need to know how our wall will deform according to some stresses or some lateral force like earthquake or blast. So this is very useful for also to introduce this result in our modeling, in our numerical model, to have like representative results. I'll move now to the structural analysis of our building. And to know about the structural analysis, we need to know about the masonry itself. As you can see here, many types of masonry are present, from the regular ones to the left, to the rubble walls, and to the double leaf wall or single leaf wall. And this is make a bit complicated to treat in terms of stress and strain and the behavior of our masonry wall. For the engineers who are here among us, the photo to the bottom right is the stress strain curve that we use to simulate a masonry wall. The right part is it's the tension, and we can see a fragile behavior of the of our masonry. And to the bottom, it is the compression part, and you can see that it is like a parabolic shape and a softening after this. I told you that the masonry is really complicated. Why? Because if we look to this photo, we can see multiple behavior of our masonry wall. The in-plane behavior, it means the crack will occur inside our wall, and the out-of-plane or overturning or rocking or behavior that we can see on the right. And till now, it is a subject of research for this kind of behavior. If we look to the bottom left, we can see that, for example, we have a normal force which comes from gravity, and a sliding force which can emerge from earthquake or blast. And our wall will behave differently from a case to another. Why? Because of this normal stress on the wall, our wall can slide or can rock or can even crack like in at a 45 degrees. So we need to know all about this so we can simulate correctly our wall behavior in masonry. Here we present the type of analysis for the engineers. This slide is dedicated for the engineers, and we can see that the major like software, commercial software in the market will stay here, will stay in the linear static analysis, some for the limit analysis. But in terms of complexity, we are doing like complex tasks from the left to the right. So here, the most useful or the most the method that we use frequently in the structural analysis for masonry buildings is this one, the pushover analysis, but a non-linear one. The commercial, when I talk about non-linear or linear, non-linear, it means that our material is plastified. So the deformation of our building is irreversible. It will come to a certain stage that it cannot come back to the initial stage. So I'm going to present some case studies that we are also conducting. And first, I will talk about this out-of-plane behavior. This photo is from Beirut. We can see a big out-of-plane failure mechanism. When we talk about out-of-plane, usually it corresponds to a failure mechanism. And we can see all this corner coming down, and to the bottom we can see many scenarios for like collapse. And here I can confess that Italians are leaders in this field, so we learn from them. Okay, even the Eurocode, the new Eurocode now is based on the Italian code, the NTC and the circular of the Italian code. So we consider a scenario for collapse, and we check the safety factor. If the safety factor is like not very big, so our scenario is possible to happen. If not, we are a bit safe. I'm trying to simplify a bit the approach of this study. Now I will move to the finite element approach. The finite element approach is really a very advanced approach that we are now trying to apply on the masonry building, and it gives like very good results. I will show you some of them. So in this model, for example, this is a building here in Beirut. We discretize the walls, so we divide the walls into small pieces, and then we search for the information in terms of stress and displacement in each of these parts. For the masonry building, we cannot go like contemporary building doing elastic calculations, so we are obliged to go to the plasticity and to see the damage in the building. So for this reason, we have to consider the nonlinearity of materials and the geometric nonlinearity. I think this is boring a bit for architects and common normal people, but for engineers, I hope you are understanding the difference between the modeling of contemporary or the historic buildings. Okay, here also it is an ongoing project. I will show you some results from these simulations. The characteristics of the building are there. The mesh size is about 30 centimeters. It means the size of each small part in this in these walls are like 30 centimeters. When we refine our mesh, we will get more precise information. So because of that, we are forced to do like a small mesh. It is a time-consuming process, but it is very useful in terms of like result. In fact, to assess this building, we did two models. One on the actual state of this building, and the second one to the right, reinforced one. What is the difference between like actual state and reinforced one? Some small details can enhance and the behavior of our building, like for example, good connection between slabs and walls, which is not the case in the Beiruti houses, can improve a lot the behavior of our building against seismic effect. Here I'm showing you, for example, the mapping of the damage mapping of the building, and we can notice many cracks, for example, in the area of the tower, and the result to the bottom right is the result of our simulation. This is the cracking coming from our numerical model, our digital model, and we can explain based on these outputs why this building like has cracks and where, and this is a very interesting output, because accordingly we can act. We can say we need to intervene here, or we need to retrofit in this area, or to treat this area or another one. Like the first model shows, for example, the one non-retrofitted, many local failure mechanism. You can see here, notice here that our walls are like moving independently, and that we have like some punching on some areas, and it is very well presented here. And here the failure mechanism of our wall. So in the actual state of our building, we can explain what would be the capacity of our building. And when we talk about capacity, in general, we talk about the acceleration, the horizontal acceleration that our building can handle. Because in Lebanon, for example, the peak ground acceleration in many places, it means the acceleration of the earthquake is like between 0.25 G to 0.3 G. And according to this result, we can compare what our building can handle if it will be like subjected to an earthquake. Here we present like the results of our building, but the retrofitted one. And you can see the connections are well done between the walls and the slab. And we can see also that our building is moving in a uniform displacement mode. To the right, to the bottom right, we can notice the existing state every wall is like acting independently from the other. As for the retrofitted model, you can really see that it is a uniform displacement. Here the earthquake is like at 45 degrees, so you can see that the displacement is like at 45 degrees. And this is what we call the box-like behavior. We need our structure to act like a box, like a global mode. The photos in the middle shows the cracking patterns if our building is retrofitted. And here we are happy to say that the cracks are distributed uniformly on the walls, not like the existing mode where we can find some local failure mechanism. It means that our cracks are concentrated in like specific places that will lead to a failure mechanism. Okay, so here it's a bit like a comparison between the original model when we have irregular displacement and force concentration, and the retrofitted model when we have the box-like behavior and better force distribution. Here also we continue, and this slide is dedicated also for the engineers, how we can know about the capacity of our building. We select some nodes on some points on the building. Usually they are selected on the top of the building, and we check the displacement versus the acceleration, or the displacement versus the base shear. The base shear is the force coming from the earthquake that will try to cut the base of the building. And here for example, on this output, we can see that our building, on the actual state of the building, is like handling 0.08 G, and when it comes to retrofitting, it will be upgraded to 0.2 G. And here it is the surface resistance of our building according to the direction of the earthquake. Like for example, in the X direction, in the 45 degrees, and the Y direction. And to complete with the engineers, this is the verification according to the Eurocode and the Italian code, where we compare our output to the response spectrum curve. And we can say as a conclusion, for example, our building is here. The resistance of our building is here. It means like it is between the orange and the red line. What does it mean? Between the orange and the red line, the damages are huge, but our building will not collapse. After the red line to the right, it means that our building will collapse. So here we can evaluate the capacity of our building and try to tell to the client, if you need to make a retrofitted building against earthquake, we need to do so. We need to intervene on the walls or on the slabs and so on. So this is a tools for decision that we can use to apply on like most of our Beiruti heritage, because really it is not so complicated, but it is not so known till date among the engineering community. I will move now for the proposals, and as I told you, we need to have this box-like behavior. So we need to unify all the behavior of our building, so all the bearing walls can participate in resisting our earthquake or our blast. Okay? So, and I will discuss a bit with you like a problem, like a case study. If we have a vault and some cracks, the photo to the upper left, what can we do to retrofit or to enhance the resistance of this vault? With the traditional understanding, like if we're gonna think concrete, reinforced concrete, we have a blind trust in modern materials like concrete or steel. And by the way, the Athens Charter in 1931 recommends the use of concrete and other modern materials and techniques. So if we're gonna think to retrofit this vault, someone will tell me we have to add some buttresses or some shallow foundation. Another engineer will come and tell me, look, we have to do some concrete jacketing here, for example. Okay, and we add some stitching, and maybe we need to make some underpinning. At the end, we will come to a solution that will make disappear the original structure or our original built heritage. So the authenticity of our building is lost, and the use of non-compatible material is also here. And if we're gonna think a bit like in a modern way, but with the spirit of our ancestors, we can come here and say simply we can add a tie rod, okay, and we monitor and we see if something will happen, if the tension in the tie rod will increase, so we think about another solution. So this is the modern understanding, which is based on the Venice charter, that recommends the use of traditional or historic materials for stabilization or restoration. And this is the traditional way of doing things. And unlikely here in Lebanon, I saw multiple case studies or like retrofitting of historic building going on this way. So we need to change the mind and go that way, to the right, not to the left. So what to do to strengthen our built heritage? First, we have to intervene to improve the wall to floor connection. It means that we need a good connection between the walls and the slab. Second, we need to improve the behavior of our arch and vaults, which are rare in the Beiruti heritage. We need to introduce a retrofitting for the floor deformability, because most of our floors are made up of timber floors or jack arch floors. Then we need to intervene on the roof structure, because the roof structure, the wall of the roof structure is acting like a cantilever. It is not well connected to the attic. And we need to improve the quality of our masonry wall. And here we can talk, and my Italian colleague Paolo will talk about the fiber net. We need to improve the quality of our poor masonry walls, because our built heritage in Beirut has like poor rubble sandstone walls. And at the end, we need to improve the connection between non-structural elements. But first, we need to know about the failure mechanism so we can say what to do. In fact, all of these photos are coming from the Beirut blast. We can notice 3 different modes of damage or failure mechanism. The first one to the left is the in-plane, where the cracks appear in the plane of the wall. In the second photo, it is the out-of-plane failure mechanism. So the in-plane is like inside the wall is still standing. However, in the out-of-plane mechanism, there is a local collapse. And sometimes we have this hybrid damage, combining the in-plane to the out-of-plane failure mechanism. All of these photos are from Beirut, and there is a lot of work to do. And here we count also on the intervention of the Italians and the foreigner expert, because they have the material to supply, and they can assist us in doing like either calculations or like an approach for retrofitting. I will move now to the first intervention on the walls, which is the basic of enhancing a wall behavior. It is called the injection. Okay, so as we can see to the top right, the sonic testing showing us that our wall in the center has like some voids, or it is weak. Maybe it is a detached wall if it is a double leaf wall, or it has voids. So we proceed by this very simple way of making some holes in the wall and injecting some lime mortar, either by gravity or by a low pressure, like less than 0.5 bar, to fill all the voids in our wall. The second one, the most famous one that can be applied here in Beirut, is the structural plastering. Here I'm showing a facade, an elevation, where the mesh, it is a fiber reinforced mesh, either glass or basalt reinforced fabric. So we put like some reinforcement on the wall from both sides, and our wall will become like a sandwich wall, like a between brackets, reinforced concrete walls, having reinforcement from both sides of the wall, but with good materials. And these two sides of the wall are connected with what we call connectors. Okay, here in Lebanon I can see some ongoing projects of our structural reinforcement. So we put the reinforcement on the walls, then we make the connection to the bottom right. We can see the connectors, the customize. I can say that, for example, Italian suppliers have their own system, but it is like similar to this. Okay, and just doing this, we can enhance the out of plane and the in plane behavior of our building to reach maybe 3 or 4 or 5 times the initial capacity, and this way we are sure that after an earthquake our building will still resist to such actions. Okay, now I'm moving to a second tool, which is to connect the walls between themselves, and here I can show a case study in Douma, but it is similar to our Beiruti house, where we are connecting walls in a Baghdadi wall. You can see the connectors, the steel connectors, going from here, for example, the wall to the right and the wall to the left, and our connectors are included inside the Baghdadi. Then the Baghdadi is closed, and we can do plastering like usual. This is a very minimalistic intervention that will enhance the capacity of our building. I move now to the wall-to-wall connection. So here we can see the T connection. So when we have two walls, two intersecting walls, and a corner one, we put these dowels. Usually we can use the fiber, or also the basalt, or also the stainless steel. And after that we can put the structural mesh. Here, for example, we have the dowels, okay, and the structural mesh and the connectors, which will make a very rigid connection for the wall. Here it is a recent application of the Beirut blast. And the basic issue, if our wall is cracked, is the stitching. The stitching is a very simple operation. We show here two different type of walls, a plastered wall and a non-plastered wall, where we introduce the stitches inside the bedding joint, and this way we can make a connection between the two separated part of the wall. This process needs to be also followed by an injection of our crack. Here we can see that our crack is filled of, for example, lime mortar. And to enhance our capacity between walls and slabs, we need to connect our beams to the outer side of the wall by doing like a confining belt, or also we can notice that for the inner walls we can duplicate our planks, so we can give some more stiffness to our slab, timber floor, and we put some braces. We connect all this system to the existing wall, and this is what we call wall to floor connection. Okay, I will show here like an example that also enhance the capacity of our last floor walls. We connect the sablière or the tie beam here. It is usually made up of timber or wood to the walls, so we can have like not a cantilever mode deformation, and also we need to reduce the torsional effect by introducing some braces or croix de Saint-André. Here I move to the treatment of foundations. This is an ongoing project, and the consultant is among us, and the contractor also. So thanks to their everyday coordination. I don't like to do so, but in some cases we need to do so. We are introducing here some enlargement in terms of concrete foundations, because we have like shallow foundation, and we are adding a floor on the top of the building. So unfortunately we need to enlarge our foundation system, and you can see some photos and the process of doing it. And in some cases also we need to underpin our walls. We can see the Micropile system introducing a good bearing capacity by friction of the soil. And in some cases, this is the best case scenario that I like to see, to do nothing on the foundation. If the soil is good and the foundation is good, we just treat the void, if there is some void in the foundations, and we plaster it, and that's it. We make a trench, we fill it by like gravel to ensure the drainage of the system, and we end it here. And I would like to ask you, after this quantity of slides, what we can do here. Do you still need to think about concrete jacketing? I think there is a lot of different solution and better solution not to do concrete jacketing. So this is what not to do if possible. Okay? And really we need a big effort from engineers and architects here in Lebanon not to do so. Okay, once the retrofitting is done, the doctor will tell his patient, please come after a while and we will check up your health again, so we can do some monitoring of the structure in terms of crack or vibration acquisition data or stress detection. And we talk now, the last decades, we are talking about the structural health monitoring. And the last slide will show you that remotely we can know what is happening in our building in terms of vibration, in terms of stress, or whatever, to give a longevity to our historic building. Thank you for your presence.